Let us look at another example and see how can we plot the Nyquist plot to investigate the closed loop system stability. The problem statement goes like this. Draw the Nyquist plot for the system whose open loop transfer function is given by gh of s is equal to k into s plus 1 divided by s into s minus 1, and find the range of k value such that system is stable. So in this problem, the open loop transfer function is given. Now if you look at the open loop transfer function, it is gh of s is equal to k into s plus 1, there is one finite 0 divided by s1 pole at origin and s minus 1. So whenever you have s minus 1, which means there is one open loop poles lying in right half of the s plane. For this kind of systems, we cannot use polar plot, we cannot use gain margin, phase margin concept, we cannot use bode plot. Whereas the Nyquist plot can be used and we can investigate the closed loop system stability. Let us see how to do that. Now, so it is a type 1 system, therefore the Nyquist path for the particular system, it will be like this. So there are again now 4 paths. First path is from omega varying from 0 plus to plus infinity, and second path is from plus 90 to minus 90 with radius r tends to 0, a semicircle, and third path is minus infinity to 0 minus when omega is varying, and again the fourth path is from 0 minus to 0 plus but the radius r tends to 0. Now each and every path we need to map into gh of s plane to get the Nyquist plot. Right, so let us take the path 1 mapping. So how can we plot the first path? So first path is nothing but the polar plot. So what is a polar plot for this? Let us take the transfer function gh of s and substitute s is equal to j omega. So therefore k into 1 plus j omega divided by j omega into we have j omega minus 1. So whenever you have j omega minus 1, its angle will be minus tan inverse of minus b by a. So that formula we will use. So what is the magnitude of it? The magnitude is nothing but numerator I have k and under root 1 plus omega square. In the denominator I have omega and again under root 1 plus omega square. You can cancel under root 1 plus omega square numerator denominator, then it is going to be k by omega. This is a magnitude. What is the phase angle? When you look at the phase angle, so numerator term is tan inverse omega and denominator s term is there j omega, therefore minus 90 and minus, because of that s minus 1 you will get 180 minus tan inverse omega. Then when you simplify this, you will be getting the phase angle phi is equal to 90 I have 180, therefore minus 270 plus 2 tan inverse omegas are there, plus 2 tan inverse omega. Minus 270 plus 2 tan inverse omega is a phase angle expression for this particular open loop transfer function. Now prepare the table, because it is a special case. We need to take 4 entries in the table: omega, magnitude, phase angle. So when omega we are taking 0 and infinity first. So when omega is 0, the magnitude is infinity, and when omega is infinity, magnitude is 0, because it's a type 1 system. Now when omega is 0, what is the phase angle? It is going to be minus 270 degrees. When omega is infinity, the angle is minus 90 degrees. Therefore, the starting angle is minus 270, ending angle is minus 90. See in between how the angles are. When you take very small omega value, then you will be having so nearer to the 270, that is 269.9. And again when you look at the ending angle when omega is infinity, and before that if you take any value omega, let us say 10,000, what will be the angle here? It is going to be 90.1 something, which means the plot will be within these 2 coordinates only, second and third coordinate. So how to draw the plot? So to draw the plot, we'll take this axis, then where is the minus 270 line? This is a minus 270 and infinity starting point, and ending point is 0, but it should touch the minus 90 degrees line. So my polar plot will be like this. So it is crossing again minus 180 degrees line. Now this is the mapping of path 1. Next, how to map path 2. We know that the path 2 mapping is 1 or more semicircles around the origin with radius r tends to 0. So we can ignore it. What is mapping of path 3? So it is going to be inverse polar plot. We know what is a polar plot. This we have inverse polar plot will be like this, and direction is away from the origin. So a polar and inverse polar, both are available. Now how to map path 4? When you map path 4, look at how many poles at origin. There is only one pole at origin, so we will be getting only one semicircle. And what is the starting point of the path 4? The starting point is ending point of your inverse polar plot. So inverse polar plot ending point is here at minus 90 degrees. The starting point of the polar plot is minus 270 degrees. So starting is here and ending is here of the path 4. So when you take these 2 points, then which direction we should take? There are 2 directions. I can go like this and I can go like this. But the path 4 direction, we know that it is always a clockwise direction. So clockwise direction means start here and go like this. So this is my path 4, which is from minus 90 to minus 270. Right, so all 4 paths are available. When you combine it, you will be getting the Nyquist plot. What will be the Nyquist plot? You can see here. So we have minus 270 to origin, and origin to again minus 90, and minus 90 to again minus 270. This is what the complete Nyquist plot. And there are 2 intersections in the negative real axis. One intersection is here, the other intersection is this point. This is infinity because the path 4 radius is infinity. This is infinity. So we need to find what will be the point here, the intersecting point, and what is the corresponding magnitude, what is the corresponding frequency. So to do that, equate the phase angle expression to minus 180 degrees. So when you equate the phase angle minus 180 degrees, it is very clear now. Minus 270 plus 2 tan inverse omega is minus 180. When you solve it, you will be getting the omega value as 1. So omega PC is 1 radian per second. Then what is the magnitude? We know the magnitude is k by omega, and omega is 1, so MPC is equal to k. So when MPC is k, what is the intersection point? The intersecting point is nothing but minus k plus j0. Minus k plus j0. Again we take 3 cases. The first case k is 0. When you take k is 1. So the first case I want to take k is 1. When k is 1, so the intersecting point is the critical point, minus 1 plus j0. So since my Nyquist plot is passing through the minus 1 plus j0, the closed loop system is marginally stable or critically stable. The system response will be oscillatory. The second case, when k is greater than 1. So when k is greater than 1, it is very clear the critical point will be thrown inside the circle, the first circle. So now critical point is inside. Then how to find number of encirclements? To find number of encirclements, you draw the line. So from the critical point towards the left direction. So if you do that, there are 3 intersections of the Nyquist plot. Let us the A, B, C, 3 intersections. So when you have 3 intersections, look at what is the first intersection direction, clockwise or anti-clockwise. If you want to know that, what is the corresponding plot? The corresponding plot is your polar, and we know that it is coming from minus 270 to minus 90. It is a clockwise direction. So we take this is the anti-clockwise direction. The first one is anti-clockwise direction. Again we are taking one more, and it is also anti-clockwise direction, 2 anti-clockwise directions. And when you take the C point, it is a clockwise direction. So 1 clockwise and 2 anti-clockwise. So anti-clockwise is 1 and clockwise is minus 1. The result will be n is equal to 1. So when n is 1, so from this n is 1 means, as a result we can say there is only one encirclement in anti-clockwise direction. That is what the result we can say. Now what is the Nyquist stability formula? Nyquist stability formula criteria formula is your z is equal to p minus n. When you look at the P is the number of open loop poles that are lying in right half of the S plane. What is the transfer function GH of S? K into S plus 1 divided by S into S minus 1. So there is a one pole lies in the right half of the S plane, which means P is going to be 1. P is 1 and N is equal to 1. So 1 minus 1 is 0. So Z value is 0. The Z value 0 indicates there are no closed loop poles lying in right half of the S plane. Case 3 again. So I want to take K value less than 1. when you take k value less than 1, the critical point will be in between the -1 point and the intersecting point. So here I have the critical point. When you draw one line towards the left direction, there is a one clockwise encirclement. So this clockwise encirclement n is equal to -1. So n is equal to -1 from this figure when k is less than 1, and we know that p is equal to already 1. The formula gives z is equal to p minus n. So p is 1 minus of -1. So 1 plus 1 is going to be 2. So z is 2. Z is 2 indicates there are two closed loop poles which are lying in right over the S-plane. So when k is less than 1, the closed loop system is going to be unstable. So what is the final conclusion from all these analysis? The stability range for the system is k should be greater than 1 and less than infinity. This is a stable condition. When k is 1, it is marginally stable. When k is in between 0 and 1, it is unstable.